It's a pleasure to be back to ICTS virtually. So I will talk about three avatars of mock modularity. So these are the three avatars of mock modularity. And actually one of the avatars, so this is work done. Basically, there are three avatars that I want to talk about is how mock modularity has come to play an important role in holography, in topology, and in duality. And these are the three papers in which I have been sort of pursuing this over the last few years. Started with the paper with Murthy and Zwegers. So these are my collaborators. So Samir Murthy is at King's College. Zwegers is now at ICTP, in fact. Arnab is a postdoc. Diksha is a student of mine. And Witten, and then Pavel Putrov, who is also at ICTP. And he will describe the third avatar in greater detail in his talk. But I will sort of set the stage and explain the general ideas. So please stop me anytime. It's good to get feedback because in this Zoom formats, it's hard to judge how people are. So if you have any questions, please do stop. So let's start with the mock theta functions. In Ramanujan's famous last letter to Hardy in 1920, he gave 17 examples. Being Ramanujan, of course, he gave no definitions of mock theta functions. And being Ramanujan, again, it was sort of some inspiration from the goddess of Namagiri, which he found very interesting with hints of modularity. For example, a function like this. Now, if a uninitiated person like you and I look at it, it looks like some hypergeometric function or something like that. Nothing special. No symmetry, modular symmetry underlying it. But Ramanujan saw some modularity. And despite a lot of work by very eminent mathematicians, this fascinating mock or hidden modular symmetry remained mysterious for almost a century until the thesis work of Zwegers, who was a graduate student of Zwegers in 2002. And the main conclusion, as a summary of a mock theta function, is that it is almost modular. So, and therefore it was difficult to characterize because it's like trying to characterize a geometric figure that is almost circular. So let me remind you a little bit about modular forms to begin with, since we are going to talk about modular symmetry and why it is important in physics and some basic definitions. So a modular form f of tau of weight k of the group SL to Z is a holomorphic function in the upper half plane, which is basically invariant under a modular transformation. So if you take out this factor of c tau plus d to the power minus k, then the function is invariant under modular symmetry. SL to Z is the group of integers, matrices 2 by 2 matrices of integers such that the determinant is 1. And in particular, one of the symmetries is of course translation symmetry. So that means you can do Fourier expansion. And you can talk about its Fourier coefficient, or sometimes they're called as Q coefficients, because you write Q as to the power 2 pi I tau. So why do we worry about modularity as physicists? Because now we know that modularity is really very important. It's of course very important in mathematics and in number theory. But in physics, there are three contexts in which modularity has appeared. One is holography, especially in ADS3 quantum gravity. If you think of ADS3, so ADS3, I'm going to now try this thing. So if you think of ADS3 as a solid cylinder, so this is a solid cylinder. Euclidean ADS3 is a solid cylinder. And then if you identify these two ends, this end and that end, then the boundary is a T2. And it's a conformal boundary because in ADS3, the scale factor at the boundary is not important. So basically you get a conformal boundary. And now the global diffeomorphisms of this T2. So you can think of this T2 as a torus at the boundary. And you can now relabel your, I mean, it's a lattice basically. You can relabel the basis vectors any way which you like. It doesn't change the torus. And that is the SL to Z symmetry. So in holography, the SL to Z is the group of global diffeomorphisms of the boundary theory. In duality, it appears in a completely different context. In a four-dimensional quantum gauge theory, the S-duality group of a four-dimensional quantum gauge theory is typically a congruent subgroup of SL to Z. And in topology, this is probably more familiar to all of us, that in two-dimensional conformal field theory, we have encountered it many times. If you're doing world sheet string theory, for example, then SL to Z is on a torus. Suppose you have a conformal field theory partition function on a torus, then SL to Z is the mapping class group of that conformal field theory, so of that torus. And therefore, physical observables in all these three physical contexts are expected to exhibit modular behavior. And so that's the importance of modular symmetry in physics. And it's not just because it's some nice fancy symmetry, it's really a very powerful symmetry. Modular forms are highly symmetric functions. And one of the important theorems that, so I'm going to quickly remind you, since maybe not everybody here is trained in world sheet string theory in the same way they were trained a few years ago. So the ring of modular forms is generated by just two functions. They are called the Eisenstein series, E4 of tau and E6 of tau, which have each of E4 has weight 4 and E6 has weight 6. So for example, what does that mean? That means you can, if you want to, if you know that some function is a modular form, say of weight 12, then there are only two possibilities. It can either be E4 cube, because when you multiply modular forms, the weights add. So E4 cube has weight 12 and E6 square has weight 12. So by a general theorem, a ring of holomorphic modular forms that we are talking about is just generated by two functions. Now you can see that it is very powerful, because if you just looked at the Fourier expansion of f of 12, it had infinite coefficients. But because of this theorem, we just need to fix the first two Fourier coefficients, and then the function is completely determined. So that's actually the power of modularity. I mean, this is also sort of behind the kind of magic that Ramanujan and people like that had. I mean, I learned this from Zwegers, who was a little bit like a modern avatar of Ramanujan. That you can prove magical identities if you know secretly that the left-hand side is modular and the right-hand side is modular. Then you just have to check a few coefficients, as you know, Ramanujan would do on a slate. And then you can prove an identity which looks, you know, extraordinarily amazing. So that's why modular symmetry is powerful. And in physics, of course, it's related to, in very many important physical symmetries are part of the modular group. In particular, in a two-dimensional conformal field theory, high temperature, because if you think of the partition function as trace of e to the minus 2 pi times beta h, where h is like the L0, then by usual arguments with the path integral, you can convince yourself that tau going to minus 1 upon tau is the same as beta going to 1 upon beta. And that's low temperature going to high temperature. In the context of gauge theory, there's strong coupling going to weak coupling. And this leads to a very powerful, I mean, as we know, in conformal field theory, there is this Cardy formula, which gives you the exponential asymptotic growth of states, or the Fourier coefficients. How rapidly do these Fourier coefficients grow? And the an grows as a function of n. And that is determined by the modular properties of this function. And in fact, there is a very beautiful exact expression, of which Cardy formula is just a small part, which is known as the Hardy-Ramanujan-Rademacher expansion. And as we know, in the black hole context, the Cardy formula, the exponential growth of states is related to the exponential growth of a black hole states because of the Bekenstein-Hawking entropy of the black hole. And then the Cardy-Ramanujan-Rademacher formula gives you all the quantum corrections to this black hole formula. So it's, if you want to go beyond Bekenstein and Hawking, once again, you are led to dealing with modularity. So this is just a brief recap of modularity in physics. Are there any questions at this point? So now, what is a mock modular form? So a definition of a mock modular form, the modern definition, for example, given by Zwegers and Zagier, and also in our paper with Murthy and Zagier, is that it's a pair f and g, where f is a holomorphic function on the upper half plane, you know, with not growing too rapidly at infinity, for example. And g of tau is a holomorphic modular form of weight 2 minus k, such that a quantity called f hat, which is a sum of f tau plus g star of tau and tau bar, and I will tell you what is g star. It is constructed out of g, but it is not g. So it's some non-holomorphic object constructed out of g, such that when you add it to f, then this f hat transforms like a holomorphic modular form of half integral weight k of some congruent subgroup of S to Z. So it's a kind of a slightly complicated definition, but the main, and then f of tau is called the mock modular form. G is called its shadow, and f hat is called its modular completion. And they are basically two properties which are sort of in conflict with each other. F is holomorphic, but it's not modular by itself. And that's why it was very mysterious. F is the kind of the theta function, this mock theta function that Ramanujan wrote down. And if you look at it, it doesn't look modular at all. It's holomorphic, obviously, because it's just a function of q, and not q bar. But there is a secret shadow of it, which is also holomorphic and modular. And you construct out of it a g star and you add it to f. Then the resulting function f hat, which is called the modular completion, this is the modern understanding, is modular. And however, it is no longer holomorphic. So that's incompatibility between holomorphy and modularity is the essence of mock modularity. And now you can see why it remained mysterious for a century, because Ramanujan understood that there was some modularity, but to see that modularity, you need to know the shadow, you need to do all this. But now we understand the mathematical characterization much better. So just to emphasize, it's like an exclusive OR. It's holomorphic XOR modular. Function f is holomorphic but not modular. Function f hat is modular but not holomorphic. And that, as I said, is the essence of mock modularity. Sorry, what happened? So another way to characterize mock modularity, which is to give it a physical interpretation, is to think about it as a holomorphic anomaly. Because as we know, in anomalies that we have encountered in quantum field theory, it's also typically something like that. You can either have some U1 global symmetry, or you can have gauge symmetry. And if you try to regularize the theory using the gauge symmetry, preserving the gauge symmetry, then you cannot no longer preserve the classical U1 symmetry. So you can sort of think of it as like a holomorphic anomaly, although the flavor is a bit different. I don't want to make this analogy is not quite precise, but the modular completion of a mock modular form is related to the shadow. So if you want to recover the shadow, then you just take tau bar derivative of it. And this is actually one way to define G stars. One way to obtain G star is sort of invert this equation. So it's like a first order differential equation. So you need a kernel for this equation. You invert it and then you can figure out. So F is in a way is the holomorphic kernel of this equation. So the shadow is both, but what you get is G tau bar. So the shadow is both holomorphic and modular, but by itself does not determine the modular completion. The non-holomorphic correction G star by itself is not modular. The holomorphic mock modular form, which is F by itself, is not modular. But the completion, which is F hat, it contains all the information because it has F in it and it has G star in it from which you can recover G. But it is not holomorphic. So a lot of these nice theorems that I told you about, that the ring of modular forms is generated by just two functions. Does not apply to f hat. And therefore, that's part of the mystery. So you can think of this as a kind of an anomaly equation, holomorphic anomaly equation. So another way to characterize mock modular forms would be in terms of their completion, that f hat is some object which is nicely modular as you would expect in some physical context, but it is not holomorphic. And if you take its non-holomorphic derivative, you get something which is not zero. Now, given how do you recover G star?
Can I just interrupt you?
Yes.
You didn't tell us what is G star, I think, no?
Yes. So I'm coming to that now here.
Okay.
This slide.
One more question though. This is G star. Okay. One more question is this F hat, which is modular but not holomorphic. It's in general complex, right? It's not real.
Yes. Yes.
Hmm?
Yeah. In general, it will be complex because F is complex.
Right.
A part of it is F, and if F is not the same as F star.
Okay.
So yeah, so that's a good question.
So may I interrupt for a while?
Yes.
Actually, you just said that the G star part was indicating the shadow portion in that in the equation, but just in the previous slide, there was a term G tau bar. What was that part indicating?
Yeah, you take G of tau. I will explain now. So you take G of tau and look at its Fourier expansion. It is Bn q to the power n. G bar tau is basically Bn star q bar to the n. Okay?
Okay. Okay.
And given this Fourier coefficients of G, which is Bn, G star is given by this equation. Okay, it looks a bit horrible, but just think of it as inverting this very simple operator, del by del tau bar. Right? Inverting del by del tau bar, you can find its kernel. You know, this is like a undergraduate problem, right? But you can write down a more explicit expression like that in terms of the incomplete gamma function. So G star is B0 bar of this plus Bn bar. So basically G star is completely constructed in terms of Bn bars.
So Atish, one more thing, these Q series, the coefficients are complex, right? These AN, BN, whatever you call it.
Yes, so therefore Bn is not the same as Bn bar.
So that's unusual, right? I mean, in modular forms, isn't it usually the case that the coefficients are just real?
No, no.
Not.
In general, not. In physics context, we always come across real because they are related to some counting problem.
No, but E4 and E6 have real coefficients.
Yeah, but you can multiply them by any complex coefficient.
You can, of course. I agree.
Yeah.
Okay.
No, and moreover, Q is complex. So if you take complex
Q is complex, but the standard E4 and E6 have real coefficients of Q to the n. So does the J function. So do delta. So does delta. I mean, all the famous modular forms have real coefficients. Right?
Yes, that's true. That's true.
So somehow here, this is going a little away from that.
Yeah, but as you can see, if I take E4 and multiply by a complex coefficient, it will have.
That I agree.
Atish?
Yes.
Yes. So you said this F hat transforms like a holomorphic modular form, but it is not holomorphic. So what does it?
It means it has the same transformation property as this. Meaning it transforms as C tau plus D to the power minus K. You can generalize this definition to say C tau bar plus D to the power minus K bar.
Okay.
That's what is meant by.
Okay. So it is a function of both tau and tau bar, and then it.
However, to get its modular symmetry, only need to multiply by C tau plus D to the power minus K. No powers of C tau bar are necessary.
Atish, can I ask following Sunil's question?
Yes.
So in the original Ramanujan's function that you showed, there the coefficients were real, right?
Yes.
But you are saying that's not generally true.
Yeah, it's not generally true. Yeah, it's an interesting question. Why is it that? I think in physics, usually we compute it as a partition function. So you always.
Yeah. I see.
I mean, it's what is called the categorification, right? I mean, you are sort of computing the dimensions of some Hilbert space, and the Fourier coefficients have dimensions of some Hilbert space.
Yeah.
That's why it's real.
Okay, thanks.
So the hero of our story is going to be this incomplete gamma function. You just remind yourself of the incomplete gamma function. This is a definition of the, so you remember the gamma function is gamma of x, sorry, gamma of 1 minus k is 0 to infinity t to the power minus k e to the minus t dt. This you remember. But now you can make it incomplete gamma function. It's also related to the error function, for example. And this incomplete gamma function appears here simply because if you take this del by del tau bar derivative, you'll pick out the right powers of t to the power k and e to the minus t. That's why it comes. So if you're trying to invert this operator del by del tau bar, you'll naturally be led to the incomplete gamma function. And this incomplete gamma function has appeared in many other contexts. For example, Sunil and his collaborators encountered it in the context of some non-compact supersymmetric quantum mechanics, etc. And it will appear again in some other contexts. And that's going to be the mathematical link which will connect all these apparently totally unrelated areas. So the incomplete gamma function is going to be important later on. So just to summarize, as a kind of a, I think it's a good analogy. Holomorphic modular form is a bit like a blue circular figure, you know. So look at the figure on the left-hand side. You know, it's not circular. It is circular, but it is not blue anymore. That is like, you should think of it as f hat. You know, f hat is circular, which is, it's modular, but it's not holomorphic. So it's like a non-blue circular figure. It's non-holomorphic modular form. And however, that little piece, red piece that if you remove the red piece, then the function, the object is not circular at all. And what you have to add to it is constructed out of another circular figure, blue circular figure. So that's your G of tau. So holomorphic modular is like, I mean, this is the kind of thing that, you know, yeah, to explain to say popular press, this is the analogy that I used. But I think it's a good analogy. I mean, it's almost correct. Now I want to explain another generalization of modular forms which we encountered, and all of you have seen it in some form or the other, but I will now again give some definition. So the holomorphic function phi tau of z of two variables on the upper half plane times the complex plane is called the Jacobi form of weight k and index n if it is modular in tau and elliptic in z. So elliptic in z simply means it is doubly periodic, roughly speaking. Of course, it cannot be exactly doubly periodic, but it's doubly periodic up to some phase. So it's doubly periodic up to some phase. So this is the phase that you should look at. And so phi of tau z plus lambda tau plus mu is almost phi of tau z, but it's up to some phase. And it is modular, again, like before, but up to some phase. So again, this is a highly symmetric function. Now it has it's a function of two variables. It's highly symmetric in tau and highly symmetric under z, under two different discrete infinite subgroups. I mean, discrete groups, SL to Z and group of translations in a plane. Now, once again, therefore, you can do a Fourier expansion, a double Fourier expansion with Fourier coefficients now denoted by Cn comma R, q to the n, y to the R. And this occurs very naturally in elliptic genera, as elliptic genera in quantum field theory. And this is the connection with topology. So consider a conformally invariant nonlinear sigma model with target space X with 2,2 superconformal symmetry with left and right super-Virasoro algebra. And one can define the elliptic genus of this theory as follows. You just take chi tau of Z as to be a trace minus 1 to the f right plus f left e to the 2 pi tau h. H left is basically L0 minus C divided by 24, etc. If you remember your conformal field theory. And as you know, 2,2 superconformal algebra has a U1 R symmetry on the left and U1 R symmetry on the right. And F right and F left are the right moving U1 charges of these two R symmetries. And since this R symmetry acts on fermions, trace minus 1 to the F right plus F left is like a Witten index. Okay, sorry. So we have minus 1 to the F right. So you have two separate, in some sense, because the left and right modes are essentially decoupled, usually at least in compact conformal field theory. You can think of left moving quantum mechanics and right moving quantum mechanics, roughly speaking, with Hamiltonian to be L0 and L0 bar. And there is a left moving U1 current and the right moving U1 current. And -1 to the F right is like the right moving fermion number. So it's like computing the Witten index of the right moving theory, quantum mechanics. It's not the Witten index of the left moving theory because you have this insertion e to the 2 pi I z F left. If z was 0, then this would be like the Witten index of the left moving theory as well. And this is called the elliptic genus for historical reasons. And it's easy to see that this object thus defined is a Jacobi form. How do you see this? Basically, you write it as a path integral. If you write it as a path integral, you know, with these insertions, without this insertion, it's just like going from trace of e to the -2 pi beta h. You know how to go to the path integral. You'll just get the final path integral of the Lagrangian. Once you have it in the path integral form, then it's obvious that the path integral has to be modular, because you can use a diffeomorphism invariant if you have the theory as diffeomorphism invariant, as is the case usually, on 2 dimensions. Then you use a diffeomorphism invariant regulator, and a conformal theory also has a while symmetry. So therefore, the path integral is both while invariant and diffeomorphism invariant. And the conformal symmetry is nothing but the global group of diffeomorphisms modulo the while symmetry. Modulo the while symmetry. So therefore, the path integral is modular. And then, if you remember, there is a spectral flow symmetry under which the superconformal algebra is invariant. If you sort of relabel what you mean by L0 and J0 in our context, H left, H right, and F right, and H left and H right, because there is a symmetry of this whole algebra, which is called the spectral flow symmetry, which basically comes from shifting the U1. You can sort of, another way to think about it is that you can bosonize the U1 current of the conformal field theory. So suppose the current is del x, then shifts of the x is the spectral flow symmetry. And therefore the path integral is elliptic. And as I explained, is the right moving Witten index that counts right moving ground states. So that's the context in which it appears in quantum mechanics. Sorry, in topology and quantum field theory. So let me now give you a couple of examples of Jacobi forms to make it, for example, the famous one is the elliptic genus of manifold K3. If you just look at the second example, B. This, by the argument that I've just presented to you, should be a modular form of weight 0 and index 1. The indexes can be computed also from the anomaly of the 2,2 theory, or the central charge of the 2,2 theory. And for a K3, the central charge is 6 because you have 4 bosons and 4 fermions. So in the large volume limit, the central charge is just 4 bosons plus half for 4 fermions. And the weight is basically the central charge divided by 6. So this you can sort of derive. Therefore, by some general arguments, you know that the elliptic genus of K3 should be a modular Jacobi form of weight 0 and index 1. And in fact, you can do some calculations in some orbifold limit and you can explicitly derive it. Sorry, there is a, this is correct. Sorry, there's a mistake.
Over 3 theta functions, right?
Yeah, it should be theta 2 square divided by theta 2 square, theta 3 square divided by theta 3 square, and theta 4 square divided by theta 4 square. These are all the theta functions which don't vanish at z is equal to 0. And eta is the Dedekind eta function. And then another one, which again is very nicely related to physics. So this is the kind of thing that you would come across, for example, if you take a D1, D5 system wrapped on a K3, and things like that. Another example is a modified elliptic genus of T4. And it's modified because in T4, there are too many fermionic 0 modes. So you have to make some insertions. And as a result, the weight is not 0, but is -2. And the index is still 1. And it is given in terms of the remaining theta function, which is theta 1 square tau of z, which vanishes at z is equal to 0. Okay, it has a double 0 at z is equal to 0. Now, once again, we have a very powerful theorem, like in the case of modular forms, that the ring of Jacobi forms is completely determined by these two A and B, but in a different way. Because now you can, instead of multiplying by just coefficients, constant coefficients, you multiply them by modular forms, which are functions of just tau. So for example, if you want weight 4 index 2 Jacobi form, then there are only, actually I made a mistake here, there's probably a third possibility, okay, but let's just proceed. There are two possibilities that you can see. One is a square, right, because you want to get index 2, and index also adds when you multiply. So a has index 1, b has index 1. So there are only three possibilities, a square, b square, and ab. These are the ones which can have index m equal to 2. And now you just have to fix the weight. The weight of a square is -4. And you want to get something which is of weight 4. So you have to multiply by e4 square. The weight of b square is already 0. So you just multiply by e4. And then you can, similarly, there will be another term which I forgot to write of ab, which you can work out as a homework problem.
No, if you have
But that is 0.
that were, yeah, that's
There is
way,
no
the
2.
weight of that is -2, right? So you can't multiply it by anything.
By maybe e6, you could multiply by e6.
Oh yeah, to make it, yeah, you could multiply it by e6.
You could multiply by
you
e6.
want to make it k equals 4, yeah, e6 ab
Yeah,
is.
e6 is ab is another option which I should have included. Okay, so now you can see how powerful is this modular symmetry. So it's not just because you like some fancy mathematics that you do this. Because once you understand this, you can just, by observation, you can write down many things. For example,
can I ask a question?
Yes.
Yes. So earlier when we mentioned the unique decomposition for just modular forms, why wasn't that I couldn't take fractional powers of the basic forms?
Sorry?
Earlier you gave an example where you had a 12 weight modular form and you could decompose into a 4 into 3 or 6 into 2, right? When you mentioned the decomposition of modular forms.
Yes,
this
just pure
E6
modular.
and so then couldn't I take fractional powers of these forms?
That's a good question. The point is that we are strictly talking about holomorphic modular forms, meaning they are holomorphic in the upper half plane. In physics, actually, you very often encounter weakly holomorphic modular forms, like 1 upon eta to the 24, not eta to the 24. And when you do that, then you don't have such a powerful theorem.
Okay, thank you.
I mean, but still, you have a lot of control, but you cannot write down the answer just by observation. So, for example, just to give you how powerful this theorem is, as I showed you previously, this elliptic genus of K3 I wrote down, and I said that you can actually do it by some explicit computation in orbifold conformal field theory. But basically, you can compute it even without lifting your finger, because if you know that it's a modular form of weights, Jacobi form of weight 0 and index 1, then by this theorem, it can only be B. And for B, there is an expression, there are many expressions, but the theorem tells you that elliptic genus of K3 has to be B up to some numerical coefficient, and which you can fix by knowing that if you evaluate it at Z is equal to 0, it should become the Euler character of K3, which is 24. So that fixes the numerical coefficient 8 in front of it. So that tells you it's a very powerful symmetry like before. But there is another useful way of thinking about Jacobi forms in terms of the theta decomposition. Basically using the elliptic property, which is essentially translations in the, translation along the torus. Sorry, translation in a plane, right? So a torus, a two-dimensional torus is thought of as a complex plane divided by a lattice. And these are the translations of that lattice. Therefore, you can define the standard level n theta functions as below, which basically have this translation property, and you can extract that out. And then what you're left with are just functions of tau alone. Therefore, a Jacobi form can be expressed as a sum over L going from 0 to 2m minus 1 of theta ml of tau and z times HL of tau. So this theorem tells you, this is a theorem of Eichler and Zwegers, that a Jacobi form phi tau of z is weight k and index m is equivalent to a vector valued modular form of h left tau of weight k minus 2. Now, what does this have to do with physics, and why should we now worry about this And yeah, why are we 1 century after Ramanujan, why are we talking about mock modular forms? So there was a very beautiful essay by Freeman Dyson when I was a graduate student, actually, I don't want to tell you, but it was in 1987, Ramanujan Centenary Conference. And he gave, I recommend that you read this actually. It's on the, you can find it on the web. It's called A Walk Through Ramanujan's Garden. And he ends that essay by saying, my dream is that I will live to see the day when our young physicists, struggling to bring the predictions of superstring theory into correspondence with the facts of nature, will be led to enlarge their analytic machinery to include not only theta function, but mock theta functions. But before this can happen, the purely mathematical explorations must be carried a great deal further. And of course, this was very inspiring. I mean, for anybody from India, Ramanujan is kind of an inspirational figure. And, and I was also young in those days. But there was really no way I could, I mean, it didn't come up in my physics research anywhere. It was a very interesting quote. But I was sort of led to mock theta functions, mock modular forms completely, you know, out of a physics compulsion. And I had to, we were led to it without sort of, you were led to it sort of kicking and screaming. We had to deal with this. So this started with a puzzle with black holes. So if you look at the counting function of degeneracies of some very special quarter BPS black holes, if you haven't studied this, don't worry about it. It's type 2 string compactified on K3 cross T2. Then what you get is a meromorphic Jacobi form. And I have introduced now all the objects that are appearing here. There's a B, if you remember, B was this elliptic genus of K3. And since this comes from some symmetric product of K3, you get some B to the power m plus 1 plus some dot, dot, dot. And then there is this eta to the 24 of tau. Eta function is the Dedekind eta function, and that has to do with some 24 bosons of the left moving bosonic string. Okay, so there is a derivation of this formula and a tau of z. But now notice that a tau of z comes in the numerator, sorry, in the denominator and not in the numerator. The quantum degeneracies are given by the Fourier coefficients of this counting function. Okay. So that is this claim, and this has been derived by various people, starting with the DVV formula, and then I think various people, including myself and people working in Paris and so on. But and the final derivation, the complete derivation, was given by Justin and Ashok. You know, carefully taking care of the zero modes that gives rise to this a tau of z. And notice that now instead of having a double zero, because a is in the denominator, not in the numerator, you will have a double pole in z. And the claim is that the Fourier coefficients of this function should give you the black hole degeneracies. But this would immediately ring some alarm bells in your mind, because Fourier coefficients now will depend on the contour, right, in the z plane. For example, in the z plane, suppose you have a pole at, this function has poles at all these points. So depending on whether you put your contour here or here, this is the z plane. Then the question is, what is going on? Sorry. Not showing. What happened? Okay, good. So the question is, what is wrong with the counting? Then there is another puzzle with instantons. So if you look at the Waffa-Witten partition function, which I think Pavel Putra will tell you more about, of n is equal to 4-dimensional supersymmetric gauge theory on CP2 for a gauge group SO3 with the coupling constant is tau, then by some general arguments you can show, because of the fact that the twisted supercharge squares to 0, you can show that d by d tau bar of this function should be 0 because it's q of something. And you are sort of, it's q exact, and therefore in this twisted theory all q exact quantities vanish. Now, just to remind you what is a Waffa-Witten partition function, don't be scared. Suppose you were interested in computing the bound states of a D4 brane wrapping a K3 and some number of D0 branes. then as you know, a D0 brane can be thought of as an instanton in the Young-Mills theory, living on the whole volume of this D4 brane. And so the bound state and what the Wafa-Witten partition function does is basically computes the dimensions of this instanton moduli spaces. So therefore, it tells you how many bound states there are of the D4, D0 bound states. So if you, and in fact, if you compute the D4, D0 bound states on K3, you get this nice function 1 upon eta to the 24 of tau because of the duality, string duality. That the type 2A string theory, in which there is a D4, D0 brane, is dual to the heterotic string, in which case the D4, D0 becomes just the fundamental string and momentum. And that, as you know, is just the 24 left moving bosons of the. So this was one of the actually striking early, I mean, and Wafa-Witten were quite taken surprised by this calculation in K3. And they kind of speculated in a sort of an prescient way that maybe there is some connection between this and heterotic string. And it turns out that it's because of type 2A and heterotic duality. But so therefore, the Wafa-Witten partition function gives you some non-trivial information about bound states of various brane systems. And that, as you know, is related also to the black hole counting problem in some ways. And now if you try to do it on some other manifold like CP2, then you fail. Because in K3, the partition function is nicely modular and nicely holomorphic as expected from this formula. You get 1 upon eta to the 24 of tau alone. There is no tau bar dependence. But if you do it in CP2, you get something not holomorphic at all. If you just keep the holomorphic terms, then you don't get modular symmetry. So it would look like S-duality really doesn't work. And Wafa-Witten used this as a kind of an evidence for S-duality in early days of gauge theories. It also was an evidence for string-string duality indirectly. But more importantly, it was an evidence for S-duality of gauge theories where coupling constant goes to 1 over the coupling constant. And if this didn't work, if by the general argument you were going to get a holomorphic piece and that is not modular, then clearly there is something wrong with S-duality. So this would be a kind of a disaster for S-duality. So it's a puzzle that you need to resolve. Then there is a final puzzle with elliptic genus. The elliptic genus of a superconformal field theory, like a sigma model on a, for example, on a K3, is again expected to be holomorphic by a general argument. And the general argument I can give you now in a moment. But for a non-compact superconformal field theory, for example, if you take a sigma model on an infinite cigar, then the holomorphic function is not modular as expected by conformal invariant. So then it would seem that you're violating conformal invariance. So in all these three cases, you see somehow mock modularity appears. I mean, some kind of holomorphic anomaly appears. And we now, looking back, we understand it as a mock modularity. And from a mathematical point of view, it's mock modularity. And now we have a nice physical interpretation of it, that it has to do with a non-compact path integral from a physical point of view. So let me explain that point of view a little bit. Why do we expect something modular? Sorry, something holomorphic. If you look at trace of, if your chi was trace of -1 to the f left, q to the, so q bar to the, so f right, q bar to the h right, then -1 to the f left, q to the h left, and then there was y to the f left. So you can forget about this piece. Just look at this piece. This is like the right moving quantum mechanics. And if you remember, if you have a supersymmetric quantum mechanics with some Hamiltonian H, which is the square of a Q charge, supercharge, and if you have -1 to the F, which is the fermion number, such that Q is odd under it, then you know that by general arguments, if the theory is compact, which means that the spectrum is compact, is discrete, then you expect that by this equation, for every fermionic state, there will be bosonic states. So Witten index of a supersymmetric quantum mechanics is trace minus 1 to the f e to the minus 2 pi beta h, let's say. Then the only thing that contributes to this are the ground states. In particular, if you call this as a Witten index W of beta, then d by d beta, W of beta is 0. So that's the holomorphic equation, if you like. So is this clear? The point is that because you're inserting minus 1 to the f, given any state f, q of f is also eigenstate of the Hamiltonian with the same eigenvalue. And because f and q of f have opposite minus 1 to the f, they cancel out in pairs. The only thing that you're left with is something that is annihilated by q. And therefore, if it is annihilated by q, it's also annihilated by the Hamiltonian. So it has to be the ground states. So the Witten index computes index ground states. Okay, and those are, and therefore the Witten index doesn't depend on what is the temperature. And this is a very powerful theorem. That's why it's a topological quantity. And in many simple cases, for example, if you take a supersymmetric quantum mechanics of a particle moving on a manifold, the Witten index is actually, which you can now evaluate at 0 if you like, is the Euler character. So, and what is powerful about this is that you can either do, and you can prove index theorems. The proof of the index theorem goes as follows. Basically, you use the fact that W of 0 is equal to W of infinity. Okay, so you define the Witten index as the index at 0 temperature. At 0 temperature, clearly only the ground states contribute because you have nothing to excite it. So this is 0 temperature, by the way. Beta going to infinity is 0 temperature. Sorry, so W of infinity is the Euler character. But now you can evaluate it at very high temperature. So this is your index. But now you can use a heat kernel expansion here. And this is how you prove that in the heat kernel expansion, you get quantities like f wedge f, and the index is some n plus minus n minus. This is how you prove Atiyah-Singer index theorem, for example. Okay. Sorry, how am I doing on the time? I'm probably very off. How much time do I have?
10 to 15 minutes.
Okay. Okay, good. I will try to wrap it up a bit quickly now. So the main point is that by general arguments, this elliptic genus, which is like the right moving Witten index, is expected to be independent of the right moving temperature, or if you like, tau bar. Whereas generically you find that it is not so. So what is wrong with? And the answer to all these questions involves mock modular forms. So let's first address the puzzle with the black holes, because that actually will lead to an important theorem, that was the decomposition theorem. And that will be the root which will actually then, some of the quantities that are encountered there will be required in Powell's talk also. So for example, the poles in the counting function turns out is a reflection of the wall crossing phenomena. I told you that the counting function for these black holes depended on which contour you are choosing. And that was a puzzle. But then we understood that if you're counting the asymptotic number of states, then generically in different chambers, you can actually get different answers, different chambers of the moduli space. So if you have, suppose, some theory on K3 cross T2, then depending on which shape and size of the K3 you're looking at, you might get different answers for black hole degeneracies. And the modular space is divided into chambers separated by walls. And there is a one-to-one correspondence between pole and wall, residues at the pole and jump at the degeneracies. But this sounds again raises another puzzle, because the quantum degeneracies of a black hole is a property of its horizon alone. And we believe that that's why black hole entropy was so important. We believe that we are sort of learning something about really fundamental quantum degrees of freedom of quantum gravity. And so why should it depend on the moduli of some K3 and so on, which is really has nothing to do with the horizon of the black hole? And so why does it depend on the asymptotic moduli? And the answer to that is now very well understood, is that because actually it's true that the black hole degeneracies only depend on the horizon of the black hole, but there are these weird configurations which are called the multi-centered black hole solutions, which exist as some kind of a bound state of two black holes. And they exist, that bound state exists only for some values of the moduli. So as you approach this wall, this dotted line is the wall in the moduli space. And what happens is that the distance between these two centers of two centered black holes sort of grows and grows and grows, and they disappear from the spectrum. And therefore, as you cross the wall, on the left-hand side, you only get the single-centered degeneracies. On the right-hand side, you get a single-centered plus multi-centered degeneracies. And that's the reason why what the answer that string theory gave you was actually correct, even though it looked wrong. So the DVV formula is correct if you interpret it correctly in this manner. And what counts the horizon degrees? So then you can ask the question, is there some way I can characterize just the horizon degrees of freedom? Because after all, if you're interested in quantum gravity, you're only interested in the horizon degrees of freedom, not this junk having to do with multi-centered black holes. And that actually is what led to my collaboration with Zwegers and Murthy. That, I was, this was happened in a cafe, and I was just, actually I think Ashok also was present at this conference. We had organized this conference in Paris, and I just invited Zwegers on a hunch that, okay, maybe he can have something interesting to say. And I told him about this puzzle about pole in this counting function, a meromorphic Jacobi form, and I asked him, does he know something about the meromorphic Jacobi forms? And I thought, okay, it's a pole, I'm sure we can figure it out. But it turned out that he said, yeah, this is actually a very difficult problem. It goes back to Ramanujan, 100 years, and only recently my student has solved this problem. And it's related to mock modular forms. So what is the connection between meromorphic Jacobi forms and mock modular forms? It goes via this decomposition theorem, that the counting function which is on the left, which has poles, can be written as a unique sum of a function without poles, which we call the polar part, and a function, sorry, the function with exactly the same poles, and a function without any poles. And the polar part is called the Apple-Lerch sum, and it has exactly the same poles in the z plane as the poles of sine of z. The finite part is free of poles, and its Fourier coefficients are uniquely determined. And so we know that for single-centered black holes, we should have uniquely determined Fourier coefficients. The decomposition is a nice physical interpretation. The polar part counts the microstates of multi-centered black holes, which are moduli dependent. The finite part counts the microstates of single-centered black holes, which is a property of the horizon. It's completely consistent with your physics intuition. And the non-trivial part of course, you can always split a function, any function, into two functions. That's not a big deal. The non-trivial part of this theorem is that both these terms actually admit a modular completion. And that will bring us into the world of modular forms. So what is an Apple-Lerch sum? You see, this function that I told you has a double pole. And if you have a double pole, so basically it has a double pole at all these points. And at that point, the counting function goes as, roughly speaking, up to some overall factors 1 upon z square. So what you can do is that use method of images. You sort of take an average over 1 upon z square and its images. All these points. And that is, you can take an elliptic average, so to speak. And that's what is the Apple-Lerch sum. So in particular, the polar part is defined by this some overall factor, which is not important, times this Apple-Lerch sum. And if you can look at it, it has this function 1 minus q to the sy. At s is equal to 0, it's just 1 minus y square, which is basically 1 upon z square. And then you add all these factors to dress it up, so that you dress it up in such a way that it has the elliptic symmetry, meaning it is basically translational invariant up to phases, much like a Jacobi form of index 2 and index m and weight 2. And the important point is that similarly, you can define psi m f. You just take out this factor p24 of m plus 1 eta to the 24. This is some overall factor, tau dependent. All the z dependence in this function phi m tau of z, and it's a mock Jacobi. This is called a mock Jacobi form of weight 2 and index m. Okay, so let me now recapitulate it a little bit. Another way to say that is that I already introduced to you mock modular forms, right? How do you characterize a mock Jacobi form? Mock Jacobi form has elliptic symmetry like an ordinary Jacobi form, but it does not have the modular symmetry. So if you do the theta decomposition using the elliptic property, you will get Fourier coefficients which are HL of tau, much like before, but they will no longer be modular, but they will be mock modular. And therefore, you can complete this, if you know the shadow, as H hat of L, HL plus D star, and that would be the mock Jacobi form. So once again, we see this.
Can we think of those HL as mock vector valued modular forms?
Yeah, exactly. So there is a one-to-one correspondence between Jacobi forms and vector valued modular forms, and mock Jacobi forms and vector valued mock modular forms.
Okay.
And once again, we see this kind of holomorphic SOR modularity, that either your holomorphic, the meromorphic Jacobi form that we started with psi is holomorphic and modular, but it has poles and it's not simple. The Apple-Lurk sum is holomorphic and simple because we could just, it's an elliptic average of a simple one over double pole. Mock Jacobi form is holomorphic and pole free, but it's not modular. And the completion is not holomorphic, not simple, but it is modular and pole free. And so there is a holomorphic equation that you can write down again. And the answer is very nice, actually. It's given in terms of the theta functions. So for the black hole problem and in many of the Ramanujan's examples, the shadow is particularly simple. If you look at the shadow, it's just theta ml of tau. So the shadow of these HLs are basically theta functions, level m theta functions. Now you can ask the question, given a shadow, what is the modular form which grows very slowly? Whose Fourier coefficients grow as slowly as possible? Because given a mock modular form, and it's, sorry, given a completion, you can always add to it another holomorphic function, and it doesn't change its modular properties. And it doesn't change the shadow because, so for example, if you take the example of m is equal to 1, it's a vector valued modular form. You should have two components. And then the following objects appear. Okay, these are the Zwegers mock modular forms. There is an H0 of tau and H1 of tau. See, if m is 1, then L can go from 0 to 1. And it is given in terms of these coefficients, H. Those are defined. There are some very fancy theoretic numbers which appear. But the main property is that, so there are some Hurwitz canonical class numbers, Hn, defined in some way, which you don't need to know. But basically you take h of 4n q to the power n and h of 4n minus 1 q to the n minus 1 4. You can show that it's a mock modular form. It has a completion. Again, the incomplete gamma function appears here. And that is what appears in the black hole story. So this is how the holomorphic and mock modularity, holography and mock modularity get related. The final statement that we come out of this is that the Fourier coefficient of the mock Jacobi forms, which are unambiguously defined, count the horizon degrees of freedom of a single centered black hole. But in many cases, the single centered black hole can come from some black holes can be thought of as excitations of a black string, like an MSW string. And the near horizon of that string will be some ADS3CFT2. So it is natural to identify, actually this identification has not still been done explicitly. It's a very interesting problem and we have been working on it a little bit. What is the, you can think of the elliptic genus of this conformal field theory of this ADS3, and that should be the mock Jacobi form. So therefore mock Jacobi forms, which are some new objects which were introduced in our paper, should be the natural objects. And as we will see, non-compact, it is related to the fact that the boundary conformal field theory is non-compact. Okay. So as I explained to you, for a compact superconformal field theory, the elliptic genus is independent of tau bar by Witten's argument. This we have already gone through. But for a non-compact Witten index, this argument can fail. Why? Because I said that Bose-Fermi, there is a cancellation between Bose and Fermi. But if there is a continuum of states, you cannot really pinpoint which state corresponds to which state. Bosonic state corresponds to which fermionic state. And therefore, what you have to do is look at the density of states of the bosonic states and the density of states of the fermionic states. And often it happens that the difference between the two is not zero. And that is the origin of the beta dependence. And this, for example, if you have a non-compact object like this, then the Dirac operator on such a manifold can have continuum of states. Okay, so in addition to having some bound states, it will have some continuum of states. And using supersymmetry is pretty easy to show that why do you have continuous states? Because you can do scattering from here, right? You can send in a state coming in like that and a state scattering off like that. And you can calculate, send in a wave going in and a wave coming out. And if you can determine the phase shifts, you can determine the density of states. And it's a fairly simple calculation in sort of quantum mechanics, scattering theory in quantum mechanics. You probably don't remember this, but from your quantum mechanics book, you can read off that if you know the phase shifts, knowing phase shifts is basically knowing the S matrix. And knowing the S matrix, you can have all the information about the theory. In particular, you can work out the density of states, and it is given by this formula. Okay. And this formula, if you just plug it in, then what you find is that my argument about the Witten index being beta independent actually fails. And you once again get this error function here. The difference between the W of beta and W of infinity is actually comes across as the error function. Sorry, I did something crazy. And you can actually do a very simple supersymmetric zero-dimensional path integral. You know, you just have one variable and two fermionic variables. This is the kind of problem that was studied, for example, by Imbimbo and Mukhi and various other people. And if you can, you get the path integral collapses because it's a supersymmetric path integral. You can do it, but you get an error function. And the error function appears also in the Atiyah-Patodi-Singer eta invariant. So all these things are getting related, and they get related because the error function is actually nothing but one example of an incomplete gamma function. So I won't tell you about the APS theorem, but the main point is that to summarize, the mock modular forms appear in physics, both in the black hole context and in the topological context, where you're computing Witten index or Atiyah-Singer index or Atiyah-Patodi-Singer index, where you can have some non-compactness in the problem. Atiyah-Patodi-Singer index is about a manifold with a boundary, but the way they proved that theorem is that they added a kind of an infinite cylinder to a manifold with a boundary to get a manifold without a boundary. And you need to do that also from a physics point of view, because usually doing a path integral on a manifold with a boundary is very complicated. So doing a path integral on the manifold without a boundary is simpler. But then that introduces some non-compactness in the problem. And that non-compactness gives rise to some correction term. And that correction term is exactly the eta invariant of APS. APS realized that if you have this non-compact piece, then the Atiyah-Singer index has to be modified a little bit, index theorem. And that correction term was exactly the eta invariant. Conversely, in the Witten index case, if you just are interested in the Witten index will have a temperature dependence. It will no longer be true that d by d beta of W of beta is 0. And that is the holomorphic anomaly equation. And that is how it enters the black hole story, that there is a non-compact confounded field theory in the boundary. And that is the source of the mock modularity in both these contexts. And as Pavel will explain next time, if you view the n equal to 4 super angles theory as coming from some 6-dimensional M5 brane, then you can actually, there is also non-compactness in the Coulomb branch of this gauge theory. And there are some additional terms so that's the reason you get a non-zero answer. So that's the summary of my, short summary of my 3 avatars and mock modularity. So maybe I should just show you the last transparency, which is this, and I should stop here.
All right, so thank you very much, Atish. So maybe we can unmute our microphone and clap. Okay, so now it's time for questions. So if you have any question, please unmute your microphone and go ahead.
Atish, in the last part of your talk, this lambda, I didn't quite get. There was this parameter lambda. When you talked about...
Sorry, I went too fast actually. Yeah, so if you have some problem like that, suppose you want to solve the Dirac equation on some manifold with a cylindrical boundary. So suppose that cylindrical boundary is of the form, this manifold is Y. Sorry, how do I? Sorry, I'm not able to get what happened. Okay. So this manifold is Y. Suppose your manifold here that you're looking at is X, which is Y times an interval going from 0 to infinity. Okay. Then to solve the Dirac equation, you can diagonal. So the Dirac operator, you can d slash, I mean, up to some, I'm simplifying a bit, but you can sort of write it as a, suppose this direction is u, del by del u plus dx dy. Okay. After some juggling, basically you can do separation of variables. If you do separation of variables, then you can diagonalize this operator first, Dirac operator on this boundary. That's the kind of thing that exactly what you do in the APS index theorem. And the eigenvalues of this operator are lambda. So basically lambda are the eigenvalues of the boundary operator. So basically you're looking at a manifold X, right, which has the form of some manifold Y cross I going from 0 to infinity. And the operator on this boundary theory, then it becomes a one-dimensional problem. So basically you can reduce it to supersymmetric quantum mechanics, because then it just becomes a one-dimensional problem in each lambda sector. And then each lambda sector, you can work out the phase shapes, and then you sum over all of them. And that's why you get this sum over lambda, which is what appears.
Okay.
So you're computing the Witten index on the theory X. But by using separation of variables, you can reduce it to an infinite number of supersymmetric quantum mechanics on just a single one-dimensional line, rather than on a four-dimensional manifold, let's say. Suppose you had a four-dimensional manifold. Y would be a three-dimensional manifold, and lambda would be the eigenvalues of that, some operator on that three-dimensional manifold. And the four-dimensional Witten index can be thought of as a sum over this Witten indices and this lambda space over a one-dimensional quantum mechanics, whose, roughly speaking, I mean, this is like how it really, see, lambda is kind of, what happens is that you can sort of double it. Yeah. Lambda is, you know, this is the kind of problems which occurred in supersymmetric quantum mechanics. If you have a superpotential, which has this tan hyperbolic kind of a shape, which goes from minus lambda at infinity to plus lambda at infinity, then it is no longer compact. And that's where, for example, Sunil and his collaborators discovered that there is a beta dependence. And that's exactly what happens in each lambda sector. And then you sum over them. So you get actually, in fact, nicely, you get in APS theorem, there is a regularized, you get a nicely regularized form of the APS theorem. The regularization is given by this beta.
Okay, yeah, all right, thanks.
Atish, I had a question.
Yes.
You introduced, you mentioned that there can be something like mock vector valued modular forms. And I'm just trying to, it's not a well-formed question, just trying to think what they might describe. So we know that rational CFT are described by vector valued modular forms, which make the characters. And the dimension is roughly the number of primary fields. Now, irrational CFT is, of course, a different story. There may be continuous family of characters, and this modular vector valued thing doesn't really work very well in the irrational case. But you seem to have some case which is in between, which is
interesting.
A finite dimensional vector, but it's mock, it's not modular. So something, presumably it's some sort of CFT which is between rational and irrational. Do you have any idea?
So it could be a rational theory, but non-compact.
So what is the definition of non-compact? I keep forgetting.
A non-compact, okay, if you think of it as a sigma model, then the manifold, target manifold is non-compact.
But in that case, why would it be rational? Is it still rational? Is that still rational?
Yeah, but I think if you want an abstract definition in conformal field theory, then if the spectrum of the Hamiltonian or the L0 operator is discrete, then it is compact.
Yeah,
so
exactly. But
can you imagine a situation where you have rational but continuous spectrum for the...
Then how can it be rational? That's the point. Rational exactly means that there's a discrete spectrum of primaries, no?
Yeah, discrete spectrum of primaries.
We should talk about this perhaps, but it has to be something in between. But I think it probably can't just be non-compact, because I think non-compact is irrational.
But there is a see. I mean, what I'm saying is that compactness and rationality are two different concepts. Meaning, if you take, for example, a target space which is a circle, right? Then for rational values of the R square, then you get a rational conformal field theory. For irrational values of R square, you'll get an irrational conformal field theory. But there is still compact.
All right. Good.
So it is yeah, but it's an interesting question, and it would be good to maybe take some simple example of the mock modular, some simple example like we have, and see if it can be related to some slightly irrational, I mean, sorry, non-compact rational conformal.
Okay, thanks.
Atish, if I can ask one more question. So you said this thing is, the analogy with holomorphic anomaly is not quite exact. What did you mean by that?
Well, there have been some papers, but I mean, what I'm saying is that holomorphy is not defined by some current, no? I mean, okay. In that sense, I mean, yeah, I think there were papers in which, no, what I'm saying is that normally in quantum field theory, you think of anomaly as some current, some symmetry.
No, but you have this is in the same spirit as the holomorphic anomaly in Calabi-Yau's or and so on, right?
Yeah.
In that same sense.
Yeah, in that same sense, but it's. But can you think of it as some kind of, you compute del mu J mu of some operator? And it's
no, not yeah, but I mean, but it just as an anomaly. That's something that seemingly should have been purely holomorphic, but because of some non-compactness and so on.
The written index, which should have been temperature independent, turns out to be temperature dependent. I mean, the simplest context, right? The simplest context of mock modularity is just this zero-dimensional supersymmetric quantum mechanics of Witten, right? It should have been all these simple tan hyperbolic kind of superpotentials in the non-compact models. That Witten index should have been beta independent, but that argument fails, and that is mock modularity.
Yeah. So my question was more, I was not insisting on the anomaly part, but the closeness to this BCOV type anomalies that you have for Calabi-Yau's, where again, there you don't have necessarily modular invariance, because the moduli space of the Calabi-Yau's is some complex. So you have some dependence on the complex structure, but and then you take derivative with respect to T bar, and you have some equation. But there was a very definite structure of that holomorphic anomaly, which is by now come very naturally. That has to do with some, there's this general flatness of this, there's this connection that you can write on the moduli space, and then there's a kind of flatness condition of that connection is what gives you that holomorphic anomaly. So
connection on the modular space of Calabi-Yau's.
So you can define a fairly natural connection using the Zamolodchikov metric on that modular space, and then it's essentially you get some nonlinear equation for the partition function, which is essentially a condition for flatness of that connection. So there was a very natural structure that the holomorphy or the lack of holomorphy obeyed a very natural structure. So in a sense, the right-hand side was sort of, it was a nonlinear equation. The right-hand side was sort of fed in, was not, in your case.
I mean, it came from, but yeah, but I think the two contexts are different. I think there it came from some degeneration of Riemann surfaces, right?
It's a similar thing. I mean, the fact that there was an anomaly is due to the fact that, again, the moduli space is non-compact. So it was very similar. But what I'm trying to say is that, just in analogy to that, maybe is there some this thing where
okay, I can probably answer. I mean, I think the two things are a bit unrelated, because there was some degeneration over Riemann surfaces which gave rise to this, right? That there was some boundary.
Yeah, the non-compactness of the moduli space integral that you have to do. I mean,
whereas here you are at a fixed value of the tau parameter on the torus. You're not doing sum over Riemann surfaces or anything like that.
No. But there are different tau. So there also you're fixing T and T bar.
You're fixing T and T bar. Yes.
Complex structure of the Calabi-Yau, but you're integrating over the Riemann surface of the world sheet.
Yeah, so I think one nice connection could be through this paper of Gaiotto and Johnson-Fried, which we used in this paper with Putra and Witten, is that, see, you have d by d tau bar of z is equal to 0. But that equation fails, and you can write it as q of something. But if it is q of something, then you can integrate it by parts. Basically, q is like a de Rham operator in this. And what is happening is that there is a boundary contribution. If you have some non-compact boundary, then the de Rham operator does not. You see, normally you say that integral of d over is 0, but integral of d of something. But if there is a boundary contribution, then it will not be 0. So therefore, you can write it as an insertion of some operator in the boundary theory. This is the Gaiotto-Johnson-Fried paper about this TMF, the topological modular form story, where they. But that equation actually we use. So basically, it could be something like what you're saying, is that you can reduce the anomaly to a computation in the boundary theory, is what I'm saying. And that sounds like what you're saying.
Yeah, I was thinking, is there a further class of mock modular forms which are kind of very special in that they are sort of coming from some integrable kind of equation, meaning they obey this holomorphy, lack of holomorphic equation. The right-hand side has sort of like, has a piece which is, the lack of holomorphy is sort of, I mean, you would probably have to translate it into some other. I'm not being very precise. Because the BCOV type holomorphic anomaly is something where del T bar of Z is something which involves del Z the whole square, or Z square. I mean, it's some kind of thing which comes like that. It's a nonlinear equation, but the lack of holomorphy is related to the original thing itself. So you get so whether there's some analog in the class of these modular forms of those kinds, where of some very natural nonlinear equation which captures the non-holomorphicity. Because this sort of thing where del Z.
No, I mean, you can imagine that suppose you have
del bar Z is sort of like Z square or mod Z square or something. I mean, something like that, which is because this structure appears very very ubiquitously in many contexts. So whether I was just wondering.
So it could be some. You are saying that it could be some special
special class of mock modular forms. I mean, because right now it's a big, I guess it's a very large.
Yeah, there is no, unfortunately, there is no classification.
There's no classification, and whether there's some way to tame that zoo by starting with some sort of a very special, imposing some additional conditions or additional things they should obey. Yeah, anyway.
It sounds like U1 dz bar of d tau is equal to.
Yeah, it's something related to Z.
Related to Z, yeah.
Yeah. And it's presumably some sort of, because the ZZ type of thing appears on the right-hand side in most of these BCOV type of this thing, that the boundary is related to two copies of itself. I mean, the lack of holomorphicity, which is kind of going to the...
it's related to square.
Like there's a factorization of the this thing. It's related to that's why you usually get a quadratic piece on the other side. And the lack of holomorphicity is sort of related to a kind of Z square. Yeah, anyhow, vague thought, but yeah. Anyway, thanks very much. That was very cool.
Okay.
Yeah, Atish, so thank you very much. So I wish you very nice time. So next week we have Pavel Putrov from ICTP at the same time, next Wednesday at the same time. So he will probably talk, tell us more about the 3 avatars. So till then, so I wish you very nice time. So yeah, bye-bye. So ciao, Atish.
Thank you. Thank you. Nice to see you all.
Thank you.
Yeah. Yeah.